Hey guys, thanks for joining me again. Tonight we're going to be talking about precipitation. As always, we're going to start with our review. So I'm going to go ahead and minimize this and share my screen so that you can see what I'm looking at. And we'll go ahead and get started on what we're going to be talking about for today. So like I said, we're going to be talking about precipitation and then things related to that. So that's a new topic for us. But it's not that bad, okay? Now, first thing I want to do is review what we talked about the last time. So one of the things we talked about was salts made from different materials. So I want an example of a weak acid, strong base salt. So for me, strong bases are easier. NaOH is a very obvious one to me. Weak acid, the most readily available to me is HF. Okay, there are lots of others, and that's going to give me an NaF. Okay, so that's the salt that I would get from a weak acid and a strong base. Okay, so we're looking at the cation from the base and the anion from the acid. So that's what we're looking at there. Now, if we want to look at a weak base, strong acid salt, strong acid, HCl, weak base, most obvious one to me is NH3. If I put those together, that's going to give me an NH4 plus a Cl minus, which you might see as NH4Cl. Okay, so again, we're looking at what happens to that base once it picks up a proton and then the chlorine that's left from the acid. So that's my weak base, strong acid salt. Strong acid, strong base. Okay, let's talk about NaOH as our strong base. HCl is our strong acid. Put those together and that's going to give me an NaCl and an H2O. Okay. And of course, I get an H2O here. Here I do not get an H2O because there is no water that's associated here. We've just moved the proton from the HCl to the NH. Well, it becomes a 4 plus. We added it to the NH3 to make the NH4 plus. Okay, so that's what we're looking at there. So the salts that I'm talking about, this one right here from a strong base, weak acid. This one here from a strong acid, weak base. And this one here, strong acid, strong base. Okay, so those are examples from there. Anything that's a strong acid, strong base listed on page 10 in the handouts, the exam handouts, it's perfectly fine for this. Anything that's not in that list is perfectly fine for the weak parts. Okay, there are tables on page 10. Oh, sorry, page 10 has the weak acids, weak bases. I can't remember exactly what page strong acid list is on, but there are tables of weak acids, weak bases on page 10. Okay, so anything that's in those lists qualifies there. Anything that's not in the strong acids or strong bases qualifies as a weak. Okay, so there's that. When we talk about is the equivalence point for a strong acid, strong base reaction less than 7, equal to 7, or 7? So if we were to talk about the reaction between NaOH and HCl, right, that's going to give me an H2O, which is a liquid, plus that NaCl. Now, the Na plus will not react with H2O to produce either H3O plus or OH minus. That does not happen. Okay, Cl minus does not react with H2O to give me an H3O plus or an OH minus. So that does not happen. So that means that my pH, when I've done this, provided that I have the same amount of NaOH as I have HCl, then my pH would be 7. And that is based on the fact that I don't have anything that's going to react with water to change that pH. If I look at the equivalence point for a weak acid, strong base. So when we talked about this previously, we had NaOH plus HF. That gave me an NaF plus an H2O, right? And the H2O I'm not worried about. What I'm worried about is this NaF. So when NaF comes apart, I get an Na plus, which doesn't react with water, and an F minus, which does. F minus can react with an H2O to give me HF back. and then an OH minus. And that's because F minus is the conjugate base of a weak acid. So since that weak acid doesn't actually want to be F minus the whole time, we're going to get back reaction to give me HF. And that OH minus generation is going to raise my pH. So that pH is above 7. Okay. When we talk about the equivalence point for strong acid, weak base, we talked about HCl plus NH3, right? And that gave me an NH4Cl. Now, NH4Cl has an NH4 plus and a Cl minus. Now, the Cl minus does not react with H2O. We've talked about that. But that NH4 plus does, because it's the conjugate acid of a weak base. So that can react with an H2O to give me, and this actually goes in both directions, an H3O plus that NH3 back. Okay, that reaction, because of the generation of the H3O plus, is going to lower the pH, and so pH is going to be less than 7. Okay, so greater H3O plus concentration, lower pH. All right, so that's what we're talking about for that. So I would expect that you can predict, based on what types of species you're looking at, what that pH would be at the equivalence point. Okay. When we talk about review 3, draw me a generic polyprotic acid titration curve. So when we talk about a titration curve, we're looking at the volume, and since we're doing an acid, the volume of base that we've added, typically something like NaOH. We're looking at pH, and we start low because it's an acid. We do one equivalence point, and we flatten out again. We do a second equivalence point. Okay. The presence of two vertical places in this means that I have two protons that I've titrated. Okay. So this is a diprotic acid because I have 1, 2. If I had 3 of them, and again, this is volume. If I had 3, that's a little higher than my graph actually goes, but the presence of 3 of those, and so I have 1, 2, 3, that would be something that is triprotic. And of course, the most obvious one that we deal with is H3PO4. When we talk about diprotic, we're talking about things like H2CO, and that should be CO3, not a CO2. That is a diprotic acid. Okay, so that's what we're looking for, is how many vertical portions of that graph do I see, right? Since this is an acid that we're dealing with, we start with a low pH and go up high, okay? So that's what we're dealing with there. Sorry, I apologize for coughing. Sorry about that. If I'm titrating a 50 milliliter sample of a 0.005 molar HCl with a 0.0035 molar NaOH, what volume of the base would you expect to need to do this? Okay, first step, balanced equation. So I'm reacting HCl plus NaOH. I know that when I balance that, that gives me an NaCl, my salt, which is aqueous, and an H2O that's liquid. This is aqueous, of course. This is aqueous. I have a 50 milliliter sample, and it's 0.005 molar HCl. And I'm using a 0.0035 molar NaOH. I want to know, what volume do I require to do this? Okay. So since I always start with the one I know the most about, because that makes my math easier. It usually means that that's the one I need to start with. So I start with the 50 milliliters of the HCl. I need to convert from milliliters to liters because molarity is moles per liter. So I need to do that conversion. So I do my unit conversion, and then I can multiply by that 0.005 moles of HCl per 1 liter. The liters go away. That leaves me with moles of HCl. I know that every mole of HCl that's used we need 1 mole of NaOH. So that gets me to moles of NaOH. And then if I want a volume, I need to divide by the molarity because that's in moles per liter. So that will cancel out the moles, 0.0035 moles of NaOH per liter. Now, that'll give me an answer in liters. I typically don't want an answer in liters, so I'm actually going to bring this down here and say, okay, 1 liter is 1,000 milliliters, and this should be stuck on the end of this calculation right there, but it doesn't fit because I didn't leave myself enough room, although I can move this, so I probably should just move it. So I can make that clear. And I still don't really have enough space, so. But this should be the 1,000 milliliters there per liter. Okay, so that's the entire calculation that I do there. And I actually don't have my calculator. Bear with me just a second. I apologize. And yes, I actually do these calculations in class when I'm in class so that people can hear me work through the calculation on my calculators, which is not always smart because I don't always do math well. But it's important that you see that as well because I make mistakes just like you guys do. So I can't expect you guys to be perfect. So I have my 50 milliliters divided by 1,000 times the 0.005 divided by the 0.0035. And then I have to multiply by 1,000 to get to the right units. And that gives me 71. And I have 2 sig figs in the 50, 1 sig fig in the 0.5. So I'm actually going to round this to 70 milliliters, where that 0 is not significant because I don't have a period after it. Okay, so that should be 1 sig fig based on the 0.005 mole, which has 1 significant digit. Okay, so that's the answer that I would report to the correct number of sig figs. Now, I don't know if I've mentioned this to you guys or not, but I only take 1 question on each test to grade for sig figs. Most of the time, it's not that important. If you really need to pay attention to it, you'll know. So I want to see that you're doing the math and not necessarily being that focused on the sig figs most of the time. Okay, so that's that. Hopefully that makes a bit of sense. Sorry, moving something because it's driving me insane. And I know that this is not the best angle, so I apologize. What is the molarity of sodium hydroxide if it is titrated by 17.4 milliliters of 0.025205 molar KHP? Okay, well, that's awesome. Now, I know the molarity of the KHP. So KHP plus NaOH is going to give me an H2O plus an NaKP. And KP has, I mean, it's an abbreviation for something. I just know that once I take the proton out of it, that's what I'm left with. Does it really matter what it is? No, not really. All it matters is I have 1 acidic proton. It's that one right there in the middle, that KHP. That's the one I'm dealing with. So I know it's a 1-to-1 ratio. I also know that I've used 17.4 milliliters of this. And I have 0.0205 molar. No, that doesn't go with the NaOH. That goes here. 0.0205 molar KHP. And I'm looking at this and I'm going, okay, they want me to calculate a molarity, but I can't calculate a molarity without a volume. So what I can do is calculate the number of moles of NaOH that are present. And that's what I'm going to do for the time being. So 17.4 milliliters, I convert that to liters. by dividing by 1,000. I then have 0.0205 moles of KHP per liter. That cancels the liters. I know there's 1 mole of KHP for 1 mole of NaOH. Now, if I had a volume, I would divide by the volume of that solution to be able to get this to a molarity. And I would divide by the number of milliliters and then convert that to liters, but I don't have that. So I'm just going to calculate the number of moles. Okay? Because then if I were given a volume, then I could do something useful with that number. So 17.4 divided by 1,000 times 0.0205 gives me 3.6. 17.4 is 36 figs. 0.0205 is 36 figs. So I have 3.57 times 10 to the minus 4th moles of NaOH. Now, do I occasionally do this and forget to give you all the information to be able to answer the question that I intended to ask you? Yeah, sometimes. It happens. If this is something that you see on a test and you don't have enough information to be able to do that, I would calculate this number of moles, and then I would say, if I had a volume, I could calculate the molarity by dividing by that volume. And that gives me everything that I need to know, because you've told me what you would do if you had the information that you needed. Okay? So that is something that you can do. Now, if you can get a hold of me and ask me about it, then that's one thing, but you can't always do that when you guys are taking tests. So if you give me an answer that makes sense based on what you do have available, you will get full credit for that. Chances are this question would probably be thrown out, but you can get additional points for doing the parts that you can do, okay? So that's my 5th review. Do we have any questions, comments, or problems at this point? I hope not. What I'm going to do at this point is go ahead and stop, and then I will get into the theory portion of the precipitation lecture. We'll start that in the next section, and I will see you soon. Thanks, guys.